Good morning. Arnold Pears is my name. I'm Professor of Technology Education and also Professor of Computing Education Research at the KTH Royal Institute of Technology and Uppsala University, respectively. Today I want to talk to you about the topic of computational thinking and why I think we should be taking that concept very much more seriously perhaps than we do today, and also to discuss some of the limitations of the ways in which computational thinking is currently being both presented and taught, both at schools and perhaps particularly at schools, but even at universities. Why is computational thinking important? Well, before we go there, if you have your mobile phone with you and you're watching this presentation today, pick up your camera, have a look at this QR code and answer a few short questions that will help us to gain a broader understanding of what you, perhaps as a practitioner, understand about computational thinking. What I'm going to do this morning, though, is I'm going to give you my perspective on computational thinking, both the definition and some historical perspective in order to allow us to move on to a discussion about why I think computational thinking in schools is part of the fundamental platform that we need to establish in order to produce future generations of democratic and empowered citizens. So what is computational thinking? Computational thinking was popularised in 2006 by Jeanette Wing, a very influential paper that she wrote and distributed, claiming that computational thinking was the fundamental mode of thinking that would be central to the 21st century. And it would be central because the world around us was becoming increasingly computerised and computationised. And what do we mean by that? We mean that the services with which we interact every day are based on computational technologies, based on computational systems, everything from your car to the social media that you use in your telephone are based on computational technologies. And the question is, how much do we really understand about those technologies? In one of her early presentations, Wing presents this image on a slide, as I have done today, and gives it as an example of how computational thinking can be applied in practical situations. And we can ask ourselves, what about this scenario is computational thinking really? Or what in this scenario could be analysed through the application of computational thinking? What's the point, in fact, with this scenario? Well, the point is that the layout of the cafeteria is remarkably inefficient from the point of view of multiple people navigating it in parallel. And so to take a computing analogy, if you thought of this as being a pipeline or an instructional system with a sequence of instructions or stations, then the way to optimise the passage of people through this space is to place them in a sort of queue where they never intersect with one another. And so you would, in fact, reorganise the stations so that the sequence of normal operations would be optimised and people could visit the stations in a sequential fashion, in a pipelined manner, each following the other, and thereby eliminating collisions and other types of overlap that produce chaos in the space and therefore contention over resources or competition for resources, which is something also in computational thinking that we would like perhaps people to understand. But is it computational thinking? So who are these people? These people, Lillian and Frank Gilbreth, between around 1890 and 1920, developed very sophisticated methods for analysing and optimising computational and non-computational systems, in particular spatial systems and production systems. So Frank Gilbreth was what in those days were called a time and motion study engineer. What he did was he analysed working processes and he optimised them. So you could say that the slide that we just viewed, in fact, is more characteristic of time and motion optimisation than it is of computational optimization, although in my analysis of that image, I did use some computational concepts, pipelining and contention over resources. But what Frank and Lillian Gilbreth did was time and motion studies. So they used time-lapse photography, they used a variety of other techniques to optimise everyday processes, to optimise production processes, and indeed even to redesign the manual typewriter to avoid key jams and to speed up the rate of typing. And Gilbreth was very entrepreneurial, so he trained his daughter, one of his younger daughters, to touch type by whiting over all of the keys of his new typewriter. And then he trotted her around to companies challenging their best typists. And his daughter was able to out-type the best stenographers of the time by about a factor of 2 or 3 with his new layout on the keyboard and the optimisation process that he'd developed. So we can ask ourselves, so this type of analysis is not new. Computational thinking as a way of analysing systems is not new. But the way we're using these things is new. When somebody presents you with a concept sketch like this, the self-driving automobile of 2030, let's say, how do we understand the concepts, the technologies, and the programmable components that go into producing this type of vehicle? How would we be able, as citizens, to judge whether or not it's safe, reliable, or even realistic to produce? Somebody claims that this will be on the road in general use in 2030. Should I believe them? Should I question them? What sorts of skills, what sort of conceptualizations, what sorts of thinking and knowledge do I need in order to be able to analyse this scenario, understand it, break it down into its components, and then make some sort of judgment about whether or not this is ethically relevant or ethically sustainable, whether this is technologically realistic, if it's even environmentally friendly. So there are many processes behind these types of production systems, not just computational, that we need to understand, but computation is central to the operation of most of these systems, and we need to understand its operation and limitations. So where I'm going is that we need to be able to explain technological artefacts. We need to understand the media around us, how it works, and whether or not claims like the one on this slide are true. Snapchat says that unlike Facebook, it will fact-check political ads. How will it do that? Well, presumably algorithmically, because they're not going to sit 100 or 200 people in a room and check every ad that's submitted to Snapchat, or indeed every snap that is posted. No, they will need to have some type of computational system behind this that will check, in some sense, the content of the advertisement against what is known in terms of a fact base, whether or not these assertions that are included in the snap might be considered to be true or false. So this would involve analysing the snap itself, extracting text, matching that text against known fact databases, a very complex process. How long would it take? Can it be done in real time? What would be the delay before the publication of such a snap? All of these things require us to think about the limitations and the potentials of computation. Thus, the relevance of computational thinking. So, computational thinking all begins with computation and computability, right? So what is computation and what is computability? So let's talk about that for a minute. Computation we've had for a very long time. Even quite primitive devices have helped us to optimise and in some ways automate computation. But computation in the beginning was a human activity. It began with counting, and the process of computation involves then the complex combination of calculations in order to arrive at a desired result. And the faster we can do these operations, the greater the scope of the problem space that we can begin to address through computation. So computation initially may involve the solution of simple types of quadratic or trigonometric equations. It may also involve the computation of tables of logarithms or navigational tables for ocean seafaring, all of which were large-scale applications of computation from the middle of the 19th century through to the early 20th century. And indeed, when computers, as we know them, were first deployed, it was thought that probably only one or two would ever be needed worldwide in order to compute the complex ballistical trajectory tables and other types of applications that were foreseen at the time. There were, of course, then considerable applications of computation in, for instance, cryptography during the Second World War. And Turing, amongst others, at Bletchley Labs in the UK, developed new methods, both of mathematical modelling and computation, that allowed those codes, the Nazi codes, to be cracked in reasonable timeframes so that they were able to intercept communications and take strategic action based on their ability to break down and decode real-time communication. So there we come into the notion of computability. What is it possible to do in real time? So computation, yes, we can do many computations, but they all take time. Computability is about what can be computed and how long it takes. So some things are computable, but not practically computable in real time, or indeed in polynomial bounded time. And these types of problems were previously considered to be something that in computer science is called a non-polynomial bounded, or NP-complete problem. That is, we cannot find the optimal solution within a reasonable time frame, and there is no upper bound, essentially, on the amount of computation that might be required in order to find the optimal solution. And this has been one of the great barriers in the advance of computing systems. So we needed to invent, as Babbage did, even more complex machines, and finally we end up with extremely complex machines which we understand very little about, which indeed are deployed potentially in our own homes. So I don't know how many of you out there are listening to me today, or indeed how many of you own a robotic vacuum cleaner. But if you do, I think you might like to have a think about what type of functionality is included in that device. For one thing, it maps your house. It also has, presumably, and quite often, microphones installed in it. So it probably knows how many people live in your house, whether you have a pet, whether your pet is a dog or a cat, how many mice are normally in your living room on a Sunday evening after you've gone to bed, etc., etc., etc. And of course, it's collecting information all the time as it vacuums. It knows that you have pets also, not just because it hears them, but because it picks up their fur. It knows that the layout of your house is the way it is because it has mapped it in order to avoid furniture. Now, all of this might seem like a harmless application, and it is until that information falls into somebody else's hands. It's quite handy if you're a burglar to have a perfect map of the property that you're about to burgle. So if I can hack into your robot vacuum cleaner, I probably can extract that map. It gives me a much better idea of how I should rob your house. In addition, quite a lot of this information is transmitted to central servers, quite often without the owner of the device being aware of this. So there are many, many aspects of these programmed systems where if we are not aware of the types of functionality and the types of technology that are being deployed, we can both be misled or we can be misleading in the way that we present them as a retailer or as a technological solution provider. So thus, we move on to the next main, I would say, difficulty with this type of technology. If we go back a slide, these types of things we could explain. They were mechanical, we could watch them work. This type of thing you can't see the internal workings of at all. In fact, if you open it, it probably ceases to exist as a functioning device. So you're not going to open it. You're not going to analyse it. You have no computing skills, perhaps, with which to try to understand its functionality. And it doesn't work in the way that computational thinking enthusiasts would like you to think that it works. What has happened over the last 10 or 15 years is that we have moved from a deterministic and reductionist model of computation. That is to say that we produce output from input via the application of an algorithm to large-scale AI, so-called AI and machine learning systems, where we match inputs to outputs, and the result of that matching process generates a model, which is the algorithm. So the algorithm becomes the output of a comparative process which we train with very large quantities of data. And this is a completely new type of computing. And not only that, a type of computing where programming doesn't give you any insight into how it works. So part of the problem with the current discourse on computational thinking is that we're approaching computational thinking from a very historical perspective. We're approaching computational thinking from the point of view that we can understand it through teaching people to program. And my claim today is that that is just not true. Learning to program will not help you to explain these types of systems, or to understand how they work, or to create them. But there are toolkits out there that will allow you to create quite sophisticated machine learning systems with very little programming knowledge, in fact, nearly none. The interfaces are nearly completely drag and drop. You pick up components, you put them together, they produce certain types of functionality. You don't need to understand how to program in the traditional sense at all in order to have a perfectly well-functioning system as a result of applying one of these design packages for machine learning systems. And this can be done by children, of course. And we have quite good research evidence to suggest that using these types of constructor kits with school children gives considerable insight into how more modern systems like this, or more like some of our more advanced systems, social media, self-driving cars, and our classic robot vacuum cleaner actually work. So, if programming doesn't help us here, what should we be doing instead? I think the fundamental difficulty with computational thinking as it's currently presented is that it's firmly located in the world of sequential imperative programming. We don't consider parallelism, we don't consider large-scale AI and machine learning, we don't try to explain classifier systems. There's much of the world of computer science, and indeed computational systems development, which is encoded into devices all around us, which we never touch when we teach programming. And it's very, very doubtful that teaching programming will help anybody to understand those systems in the level of detail that would allow them to make informed choices about the deployment of such systems in their everyday lives. So, if computational thinking as conventionally defined doesn't help us, and teaching programming at schools is something we should reconsider, what should we do instead? And there's quite a bit of research that suggests that whilst teaching programming gives you certain types of insight into sequential problem solving, we need to broaden our perspective very considerably if we're going to educate future generations of citizens with the computational thinking skills that are required to analyse their world and the world that will be built in the next 20 to 50 years. Programming is on the way out, and programming-based computational thinking is not going to help us. So what should we be doing? Well, even if there are limitations with the current model and the current way that we're going about deploying computational thinking, either as a school subject independently or through embedding it in existing subjects, as is being done in Sweden, Finland, and some of the other Baltic countries, we will gain some power from the current methods. But whilst this equips citizens in some ways to understand the more traditional computing systems like the ones on this slide, it will only help them to explain the world around them if they understand the limitations of computability and what the computer really is. So what types of thinking, we can ask ourselves, are fundamental in addition to or in collaboration with, or should they be replaced by, computational thinking? How do we define mathematical thinking? There's been a lot of talk about critical thinking. What is critical thinking to us? How do we engage critically with the world around us? How do we analyse sources? How do we think about the nature and the ethical implications of decisions that we make every day? And what do we really think about computation and computational thinking? So I've been doing some quite serious thinking about this, or at least I've been doing as serious thinking as I am capable of. And in the context of that thinking, I tried to produce a chart, and it's on the next slide. You won't be able to read the details, and it's not the intention of the slide for you to be able to read the details in any way. The only thing you need to take away from this slide at this point is that the green circles represent what is currently covered in the computational thinking curriculum. So you'll see that there is a couple of green circles in the middle of the diagram, and then 2 or 3 others to the left-hand side. Everything else on that slide, I would claim, is highly relevant to computational thinking, but is not covered in our curriculum in any way, shape or form. So my claim here is now that our understanding of computational thinking will be fundamental only when we can define what it is. So thus, the attempt on the previous slide. Explain to other people how it's useful. And this is crucial. We need to be able to justify the inclusion of computational concepts and programming in our curriculum through explaining to our society and to ourselves what it is this contributes to empowering future generations of citizens. How is it useful to them in their everyday lives? If this is not useful to them, then there's no point teaching it at school. We have a pretty good understanding, I would say, of why it is we teach mathematics, biology, chemistry, humanities, languages in our schools. But if we're going to add something new, some new type of thinking, and we argue that that type of thinking will be fundamental to empowering future generations of citizens to sustain the democracy of which we are so proud, then we need to be able to explain to people how it's useful. And it must include things that go way beyond basic programming that we are capable of deploying in schools today. Learning to write some loops in Scratch and animate a sprite on the screen doesn't help you to understand how self-driving cars work. And there is no way that you can make a leap of intuition from that type of conceptualisation to the complexity that you would need to understand in order to understand something about self-driving vehicles, or even how social media works. So we need to be able to define this thing, we need to be able to explain why it's useful, and then we need in schools to be able to utilise the unique properties of this type of thinking to help people to analyse and understand the world around them in order to make high-quality decisions that influence our future. Why is this central to the school curriculum? Because the school curriculum is the motor that drives the development of our society. The school education that a pupil receives sets the foundation for our industries, for how we develop and deploy systems in our society, and how we engage with the great challenges that our species faces in the future. So it's crucial that we understand the nature of these systems and how they can contribute to both endangering our future and preserving and empowering our future. So, computational thinking, to sum up, at a basic level, is all about understanding how programmed technological solutions are structured, constructed, and can help us to understand and explain them. So we need to understand the structure of new types of systems. I already mentioned that. Programming is not enough. Programming is strongly rooted in this reductionist and sequential way of thinking. We need to be embracing parallelism. We need to be embracing concurrency. And in a sense, we've constrained ourselves. Programming and computation existed, as I said in the beginning of the talk, way before large-scale modern computers were invented. The first navigational tables in Britain were actually produced by computers in the early 1800s. Computers, I hear you say. What type of computers? Yes, those computers, as they were called at the time, were English clergymen in the countryside. A programming central in London sent out to these computers instructions and data. That is to say, they were sent out some basic arithmetical and mathematical procedures and a set of numbers that they were supposed to apply them to. And they performed these calculations. They arrived at a solution which was a component of a navigational table, and they sent their solutions back to the central computing centre in London. So this is, in a sense, the first parallel computer. We had very specific and unambiguous instructions that were sent to a large number of computing entities that all operated in parallel independently, returned their results to a central processing facility where they were compared by other people called comparators in order to arrive at an understanding of whether a given solution was correct and could be backed up, because these solutions were in fact generated in parallel by several computers, and then they were compared in order to eliminate human error. So much of this algorithmic foundation that we rely so heavily on doesn't require the computer in the modern electronic sense at all. It requires a way of thinking about the structuring and the solution of large-scale problems. And that type of thinking can be applied to all sorts of domains in everyday life. However, in relation to the realisation of designs in hardware or software systems, this is something that we need to then build onto this more physical understanding of what computational thinking is. Because increasingly we are not doing computation in the same way as the navigational tables were compiled a couple of hundred years ago. Everything we do today is happening in mobile phones, in programmable devices of all sorts of different natures all around us, bank telemachines in the wall of your bank, different types of online service that you use to gain access to films, to gain access to other types of personal data, to register your tax return. All of these types of systems require design and implementation, and it is only through equipping people with these basic computational skills from all sectors and all walks of life that we will have an appropriate representation of people in the design offices that construct these systems for the future. And only through doing so, in an ethical framework, will we be able to address some of the major challenges that lie ahead of us. So, computational thinking, a fundamental pillar of democracy, because it helps us to understand and structure the world around us, helps us to formulate algorithms where they are relevant. It allows us to implement and design hardware and software systems, and hopefully in the future, through the deployment of this type of thinking in the school system, we will have much more sophisticated thinkers as engineers who will be designing these systems in a more truly inclusive manner in the future. And it's really crucial also that even if you don't go on to be one of the people who builds one of these systems, that you are able to observe their operation and understand and reflect about those systems and their their impact on your everyday life. And in doing so, as we work on this in schools, I would argue that all of the examples we use must be relevant to pupils' personal experiences of computation, the devices that they carry with them in everyday life, the way that they interact with their friends through online platforms, both the advantages and the disadvantages. Sometimes these systems are of enormous value to the young, stripping away barriers, opening up the world in new ways. I was surprised to discover some years ago that one of my daughter's best friends, she's never met, is a girl in Japan, and they share a hobby, which is a love of a particular Korean rock band. How would that have been possible without these technologies? But at the same time, there are enormous dangers. You don't really know who people are. You don't really know where they are. These online environments are, in some sense, completely alien to many of us, and they need to be understood both by ourselves and by those who will both use and develop them in the future. And I'm quite sure that we haven't seen the end of that development yet. So thank you for your attention. And if there are any questions from my limited audience, I should be delighted to answer them. No? You're all stunned.